the parametricity theorem says that any fully parametric function satisfies a certain law. And in many cases, this is a naturality law, but in some cases it is not. It's a different, more complicated law. Relational parametricity is a method for proving the parametricity theorem. Also, relational parametricity gives a more general law than naturality law, and that can be used to prove other properties. All of this, of course, concerns properties of fully parametric functions. The main references in this area are the Reynolds and Wadler's papers. The paper of Reynolds, you can see the links if you get the slides, was very difficult to understand. I couldn't really understand most of what's in that paper. Wadler's paper, Theorems for Free, I could understand some part of it, but I could not see any proof of anything that I could make sense of. And also I could not see how I can apply that information to derive other properties. And so I believe it's safe to say that those papers are hard to understand, and they're also limited in scope. For example, they do not talk about what to do with arbitrary type constructors. And unfortunately, there are very few pedagogical tutorials on the subject of parametricity theorem or relational parametricity. So there are some that I have put in here. You can get the links if you download the slides. So in this part of the tutorial, I will talk about motivation for relational parametricity. The parametricity theorem says that every fully parametric function satisfies a certain law. Now, in many cases, that law is a naturality law. In other cases, it's a different, more complicated law. Relational parametricity is a technique, a method for proving that theorem. Also, relational parametricity gives a formulation of the more complicated law in the general case, which you can use to prove other properties. Naturality laws are sometimes not strong enough to prove properties of fully parametric functions. The main references in this area are the papers by Reynolds and Wadler. The links here you will get if you download the slides. Unfortunately, these papers are quite difficult to understand. I think it's fair to say. I couldn't understand most of what that paper was saying about parametricity, and I couldn't understand a large part of Wadler's paper. And I also didn't see how I could apply that information to derive other properties. And I also couldn't understand how they prove anything. So unfortunately, there are very few pedagogical tutorials on this subject. My tutorial is trying to fill that need. I put here some tutorials, but they're not really satisfactory in my view. I'm pretty sure that a lot of people would have a lot of trouble understanding this material. So in this tutorial, I derive all the results, all the main results from parametricity theorem and naturality laws and other laws, but I'm not following either of these papers or these tutorials. It's my own tutorial where I only explain the minimum necessary knowledge. I do not introduce a lot of concepts, a lot of notation, unless it is absolutely necessary. So what is the difficulty in the proof of naturality laws? One difficulty is that naturality laws are formulated via these liftings, the F map and C map. So here is a general formulation of a naturality law. But this only works if the type constructor is covariant. If it is not covariant, then you cannot lift a function of type A to B to a function of type f of A to f of B. If it is contravariant, you can lift in the opposite one. But in general, when you take some code, you need to look at some parts of that code. The type of those parts is going to be neither covariant nor contravariant. So also there are some function type signatures that are neither covariant nor contravariant. Like, for example, the fold left function. Let's formulate this type signature. This is not of this form where f and g could be any type constructors, both covariant or both contravariant. This type signature cannot be put in that form because the type parameter a occurs in covariant and contravariant positions at the same time in a difficult way that you cannot really transform this in some equivalent way so that it becomes a natural transformation or a function of this type signature. So then you ask, well, what is the law that this function must obey? That's similar to naturality law, but maybe more complicated than naturality law. What is that law? How can we even write it down before we talk about how we prove that law? So imagine that also you take a code of this function. You want to prove that the law holds. And some parts of that code you would have to prove by induction that given that those parts satisfy the law, then the whole code also satisfies the law. But partial code will not necessarily have this type signature, or it could just not even be a function. What is the law that it satisfies? How do you even formulate the inductive assumption for the proof? So these are the main difficulties. And we will have to formulate a more general kind of naturality law. Now, just to remind you that naturality laws express the programmer's expectation that the function code that is fully parametric works in the same way for all type parameters. Now, certainly we have the same expectation here, but how do we express that expectation in terms of a law, of an equation, or some other mathematical relation or expression? So the solution is based on three rather non-trivial ideas. And one is that we need to generalize from functions f to arbitrary binary relations, which I write like this. R, a binary relation R, has the type relation between values of types A and B. So instead of saying it's from A to B in one direction, a relation is a non-directional object. So functions are subset of possible relations because there's a graph relation, so-called, and the graph relation means f of A equals B. So A, B are in the graph relation if f of A equals B. So functions are many-to-one relations because many different values of A are related to a single value of B. we need to generalize that to arbitrary many-to-many relations between values of types A and B. And so instead of writing f of A equals B, we will write more generally that A and B, values A and B, are in a relation. And this is going to be non-directional. So it's neither from A to B nor from B to A. It could be a many-to-many relation. So that is the first step. We need to pass on from functions, which are many-to-one relations, to arbitrary many-to-many relations. Second step is to realize that once you do that, you can always lift a relation between values of types A to B to a relation between values of types f of A and f of B. The lifting function I denote by RMAP, by analogy with fmap. So fmap lifts functions and RMAP lifts relations. Now, the interesting and very non-trivial fact is that even when the type constructor f is neither covariant nor contravariant, you can still perform this lifting. So if you begin with some relation here, then you always can construct the corresponding lifted relation here. And in the next parts of the tutorial, I will be defining explicitly how that lifting needs to work. And final third step here is that instead of formulating the naturality law via functions, as we did before, as we did here, we need to formulate it via relations. So we write a relational naturality law, which is very similar, except that we don't have functions anymore here and here. We still have functions here. So there's a function t with a type parameter, which goes from f of A to g of A, or from f of B to g of B. But the values of types f of A and f of B are no longer related by a function from one to the other. It's just an arbitrary relation between them, arbitrary binary relation. And here's also a binary relation. And now these are actually not arbitrary. So if you take any relation from between A and B, then you need to lift that relation first to F, and then you lift that relation also to G. And then you get these two other relations, which you need to impose. So the naturality law is that, if you write it in words, for any relation R between A and B. Now I'm going to talk more quickly between A and B, instead of saying a relation R between values of types A and B. So that's the only kind of relations I'm going to talk about in this tutorial. So I'll just say relation between A and B to be quicker. So for any relation between A and B, for any value fa of type f of A and fb of type f of B, such that these two values are in the lifted relation RMAP of R, then we require that the results of applying t to these two values, so t of f of A and t of f of B, must be in the relation RMAP G of R. Now this is, I will motivate why this makes sense, but this is a generalization of the naturality law, where you just replace functions here by relations. In the naturality law, you have a lifted function here from fa to fb, from ga to gb. Here we have a lifted relation. So that is the generalization. And it turns out that when f and g are both contravariant or both covariant, and R is a graph relation for a certain function, then this reduces to the naturality law with functions, to this law. All of this we will prove. I'm just motivating that actually the relational technique is going to solve the difficulties with proving parametricity results and naturality laws. So once we get to that point where we can write down a law satisfied by values t of any type whatsoever, not necessarily functions, not necessarily covariant, contravariant, that's where it will be much easier to prove this relational law, which we will have to generalize a little more, and then the proof will be not difficult. So here's why naturality law, which looks like this, really corresponds to the relational law of this kind. So suppose we start with this naturality law, and we want to just rewrite everything in terms of relations. We're not going to change functions into relations, or rather, we're going to just use graph relations for everything. So we still have a function f, we still have a covariant f and covariant g. For any fa and fb, we have this diagram. Now, instead of saying we start with f of a, we compute this, and then we compute this, and we compute this, and the results must be the same. That's what we usually say with commutative diagrams. Instead of this, we're now going to say for any values fa of type f of a, fb of type f of b, as long as they satisfy this equation, then the values t of fa, t of fb satisfy this equation. It's exactly equivalent, because if they satisfy this equation, it means that fb is completely determined by choice of fa, and so then this is just a naturality law written out a little longer. But this allows us to use relations instead of equations. So we say, instead of writing this equation, we say fa, fb are in the graph relation of this function. Now, this is the definition of the graph relation, which I showed you here. So we say for any function f, values a and b are in the graph relation of that function, if and only if f of a equals b. So then we just write, instead of this, we write fa fb is in graph relation, and then t of fa, t of fb must be in the graph relation of the lifted function f. Now, we will also expect that when you lift a function and you take the graph relation of that, it's the same as when you first take a graph relation and then you lift with the relational lifting operation. Right? So now we expect that this is true. This needs to be proved, and we can prove that. But this is something we expect to happen when f is covariant. We expect that the relational lifting operation is compatible with the f map for a covariant type constructor. So then we can just replace the graph relation f by an arbitrary relation r, and that's how we generalize. So up to this point, we just wrote relationally the same naturality law as before. Now it tells us how we can generalize that naturality law, why we put here the lifted relations. So this gives us a motivation of why it makes sense to start considering these sorts of laws for relations. So now let me define a little more formally what relations are. Programmers are familiar with relational databases, so where a relation between A and B is just a table with two columns. The values on these columns must be of types A and B. And then a row in the table means that the value A is related to the value B. So the table contains a certain number of rows, and each row gives one particular pair, and all the rows give you all the pairs that are in the relation. So mathematically speaking, a relation is a subset of the product of the two sets. It gives you just the pairs that are related and not any other pairs. So this set contains all possible pairs of A and B, and this contains only the pairs that are in the relation. So we can arbitrarily choose certain pairs, and this choice defines the relation. And so we write AB is in R, mathematically it's the same, just in a different notation. That's to say that the pair AB belongs to this subset R, which is a subset of the product of A and B, Cartesian product of A and B. So defined in this way, relations can be many-to-many, because you can always have any kind of number of different values of A with the same B and different numbers of B with the same A. You're not limited anymore. While with functions, you're limited. You have to be many-to-one. So a function of type A to B generates a graph relation, which is of this type. So we write relation types like this. And two values are in a graph relation precisely when f of A equals B. An example is if you take an identity function from A to A, the graph of that gives an identity relation. And so two values, x, y, are in this relation only when x equals y, and both have type A. And here's an example of a relation that could be many-to-many. Let's take any two functions of types A to C and B to C, and we define a relation called the pullback relation, which is going to be of type relation between A and B. And it's defined by saying that A and B are in that relation if f of A equals g of B. So now this is an equation between values of type C. So this is a very general construction which could give you many-to-many relations, because f could map many values of A to the same value of type C, and g could map many values of type B into the same value of type C. And so this could define very easily a many-to-many relation. And so this then is not going to be a graph of any function. So this many-to-many relation is not equivalent to any function from A to B or from B to A. Now, it's important to use certain relation combinators for proofs of the parametricity theorem. And so now I'm going to define those combinators. If I have two relations, R and S, between some arbitrary types, then we can define new relations based on them. So first is the pair product. So that is a relation between pair AX and pair BY. And this is defined just by saying that the first elements of the pairs must be in the first relation, and the second elements in the second relation. The next construction is a pair coproduct, or a pair sum. And that gives you a relation between coproduct types. And the two values are in this relation only when both are on the left, and then A and B are in the relation R, or both are on the right, and then X and Y are in the relation S. So this is kind of reasonable. Now, the next combinator is quite non-trivial, although its definition looks simple. It's a pair function mapper. So it takes two relations and gives you a relation between function types. So there are two function types, A to X and B to Y, and we've had a relation between A and B and a relation between X and Y. So now it is defined by saying that two functions, f and g, of the types A to X and B to Y are in this relation whenever two arguments are in the first relation, then the two results are in the second relation. So here's a diagram. We take two arguments, A and B, arbitrary A and B, as long as they are in this relation R. When you map them into some X and Y using the functions f and g, and then those results must be related by S. If that is true for all values A and B here that are in R, then the functions are related by this function pair mapper. So the pair of relations becomes a relation between a pair of functions. Now, this definition looks simple, but actually it's quite complicated, to understand and to use, because this is not an equation. It is not that f and g satisfy some equation. It's not in this form. For all a and b that satisfies some condition, f of a and g of b must satisfy another condition. Now that's quite a different logical statement than just f of something must be equal to g of something. And this is for arbitrary relations. So these relations are not necessarily function graphs. So you cannot express a through b here or b through a and substitute it here. So they're really, it's really not easy to reason about such relations. But this is key. This relation is key to why you can lift relations to arbitrary type constructors, even when those type constructors are not covariant. This is because you can always lift a pair of relations into a relation between functions. And this is not possible with ordinary functions. You cannot do that. You cannot take a function from a to b, a function from x to y, and get a function from a to x to b to y. That doesn't work. And so this is this construction is why essentially relational lifting is more powerful than lifting of functions, and that's why it solves the difficulties with parametricity. And the final very simple combinator is a reverse relation. So if you have a relation R between A and B, then the reverse relation is between B and A, and it's defined just by reversing the order of the arguments. It's equivalent to the relation R in its information. You can always reverse back. Reverse of R is just the same as R. So at this point, I will stop, and in the next part of the tutorial, I will define how the relational lifting works. That for any type constructor F that is fully parametric, and for any relation A between A and B, you get somehow to define a relation between F of A and F of B.